So then we have absolute dating. So earlier we talked about relative dating, which was the comparisons between different geologic events and different rock layers and saying what's older, what's younger. Absolute dating takes into consideration actual ages using numbers. So scientists relied solely on relative dating methods until the discovery of radioactivity at the end of the 1800s. A scientist named Marie Curie worked on the discovery of radioactivity. Absolute dating includes methods for determining the actual ages for rock units or ages of events, like volcanic eruptions, for example, ancient volcanic eruptions. And then you describe those ages as years before present. So absolute dating relies on radioactive decay techniques. So you use radioactive isotopes, for example, carbon-14, and I will go over how to do that. Okay, so here are these two friends again. Hey, Sammy, how old are you? And then the response is 22 years and 3 months old. Okay, so just a comparison to their previous conversation. This conversation has actual dates involved. So that's absolute dating. So absolute dating requires the use of isotopes that are radioactive. So what is an isotope? Isotopes are atoms of the same element that have different amounts of neutrons. So you have carbon-12, carbon-14, and carbon-13. They all have the same number of protons, which is the atomic number, but then they have different numbers of neutrons. So their atomic mass number changes, which is the number of protons plus neutrons. So carbon-12 and carbon-14 are stable atoms. Carbon-13, oh, sorry, that actually is supposed to go over here. Oops, sorry. Carbon-12 and carbon-13 are the stable atoms of carbon. Carbon-14 is the radioactive isotope of carbon, which means that it decays, it loses particles over time. So radioactivity, these are some definitions here. Radioactivity, some isotopes are unstable and their nucleus will spontaneously decay, transforming to other more stable isotopes of elements. Most isotopes of elements are stable, but you do have some that are unstable. For example, the carbon-12 and carbon-13 are stable, and then carbon-14 is unstable. Okay, so most atoms have stable isotopes. The parent isotope is the unstable radioactive isotope. The daughter product is the isotope that results from the parent isotope decaying. The half-life is the time required for 1/2 of the radioactive nuclei in a sample to decay. And here are two different types of nuclear decay examples. We have alpha emission. That's when the nucleus of a radioactive parent isotope emits 2 protons and 2 neutrons. 2 protons and 2 neutrons, collectively we call that an alpha particle. So that's alpha emission. Beta emission is when the radioactive parent emits an electron, and that's called a beta particle. So isotopes that are unstable actually lose particles. They emit particles into the environment, and that's how they decay. So some isotopes undergo only one decay step. So for example, one step of alpha emission, and then it becomes a stable isotope. But other isotopes need to go through a few steps. Okay, and then I have an example here. Rubidium-87 decays to strontium-87 through only one beta emission. So one emission, and then it is stable. But then some isotopes undergo several decay steps. So like uranium-238 ultimately will decay and become lead-206, but it has to go through several alpha and beta emissions first. So here you have uranium-238, and then this symbol here that looks kind of like the letter A, that's an alpha emission symbol, that's an alpha. Okay, so it shows you after an alpha emission, it becomes thorium-234. Okay, and then you have all these steps. Okay, so you follow the arrows. Now, radon here, I just put like a little note here. Radon gas is actually, it's a radioactive gas that can cause environmental issues. So some people live in areas where they have to get radon tests done in their homes to make sure they don't have buildups of radon gas in their house. The radon would come from the decay of isotopes in rocks in the bedrock underneath the house. For example, that's one way that you would get radon. Okay, so here's the radioactive decay curve that shows the number of isotopes and the number of half-lives. So you start out at 0 half-lives. You start out with, for example, 16 parent isotopes. After 1 half-life, you have half of those isotopes have turned into daughter isotopes and they decayed. So half-life is the amount of time that is needed for half of the nuclei in a sample to decay from the parent to the daughter. Okay? So after 1 half-life, you no longer have 16 parent isotopes. Half of those have turned into the daughter isotopes. Okay, and then after 2 half-lives, you now have 4 parent isotopes left and 12 daughter. Okay, so that is the radioactive decay curve. Now, the actual number of years involved with these half-lives changes depending on what isotope you're talking about. So uranium-238 and carbon-14 are going to have different half-life years, like amount of years that is a half-life. So here's an example of using radioactive isotopes to date igneous rocks, and you could read more about this at this link here. Here is a picture of a zircon crystal. So radioactive parent atoms can become incorporated into the crystal structures of various igneous minerals. For example, radioactive parent isotopes can incorporate in zircon crystals as zircon crystals form from cooling magma, like granite, for example. All of the daughter atoms present in igneous rocks, therefore, were formed after the magma cooled and formed the igneous rock. Because daughter atoms are unable to go, like if there were daughter atoms in the magma, they're not going to go in the zircon crystals. The zircon crystals are only incorporating the parent isotopes. So when you go and date an igneous rock and you find any daughter atoms, those formed after the magma cooled and turned into the igneous rock. So you can therefore date how old that igneous rock is or when it formed. So you can use equipment called a mass spectrometer, which actually counts the parent and daughter atoms in crystals. And then you get the ratio of the parent to the daughter atoms. And then using the half-life number, you can calculate the age of the rock. So zircon contains uranium and lead atoms. So then you would count the uranium and count the lead in the zircon crystals. And then using the ratio from the radioactive decay curve, you can determine how old the rock is. So this is what a mass spectrometer looks like. It's just this huge equipment, okay? But inside, it's really complex, but it's actually a simple process. So first of all, you would have to prepare the samples. So you take an igneous rock and you crush it, and then you would search using like a microscope and tweezers, you would search for little zircon crystals. And then you prepare the zircon in such a way that you can put it into a spot of the mass spectrometer where you have ionization of the material that you put in. The sample goes here, it ionizes the sample, and then the ions are shot through this curved tube. And depending on the weight of each ion, they will move through the tube in a different way. So you collect the different ions in different spots, and then the machine counts them. So it separates the ions by weight because the parent and the daughter isotopes are going to be different weights, and it counts them. So then you get the ratio, and then you're able to use the half-life number to calculate how old that rock was or how long ago the rock formed. So then carbon-14 is used to date organic material like tree bark or leaf fossils or woody material that you find in sediment. And that's because carbon-14 is constantly being formed in the upper atmosphere. And then organisms incorporate carbon dioxide through respiration. So organic materials have carbon, but you're constantly, any living organism is going to be incorporating carbon dioxide into its cells and interacting with the atmosphere. So then once a plant or animal dies, the cells stop taking in new carbon for new carbon dioxide. So you're no longer taking in new carbon-14. So then that starts the time of when carbon-14 in the organism's cells decay back to nitrogen-14. So the half-life of carbon-14 is 5,730 years. So it's useful as an isotope to date back to 70,000 years or younger. So you can't use it to date dinosaur bones or anything that old, but if you find a seashell fossil or if you find woody material, you can date that. Archaeologists and anthropologists use carbon-14 dating to date things like linen and cloth and scrolls, like paper scrolls, things like that. Here's a table that shows common isotopes used in absolute dating. So here are the parents, the daughters, the half-life numbers, and then the minerals that you could use that contain those isotopes. So here I was talking about lead and uranium. Here's uranium-238. The half-life is 4.5 billion years. And you would use zircon as an example. Okay, and then I added carbon-14. That was not on the chart. So how do we date sedimentary rocks? Radioactive dating techniques are not very useful for dating sedimentary rocks. Why not? Because the sediments are made up of pieces from older pre-existing rocks. So like if I were going to take a conglomerate rock and try and determine the age of the conglomerate, all I really would be getting would be the age of the materials that are in the conglomerate. And then I might find that the pebbles are very old, but the conglomerate might be a lot newer. So to determine the dates of sedimentary rock layers, geologists have to rely on ages derived from other materials that they find in the sedimentary rock layers or sedimentary deposits. So you would look for volcanic rocks, such as ash falls and lava flows, and then use potassium argon isotopes from the ash to figure out a date. But then all you really would be doing would be figuring out this lava flow is, let's say, 1 million years old. So any sediment on top of the lava flow would be younger than 1 million years old. And anything below that volcanic rock layer would be older than 1 million years. So that's all you really could do, but it gives you an idea of age. You can also look for igneous intrusions and then date those. But again, then you would be using relative dating and saying, okay, these rock layers are younger or older than the igneous intrusion, depending on the layout, depending on the relative dating rules that you see in the rock layers. Also, we could use fossils. So we could use index fossils, which we talked about last time, like the graptolite fossils, for example, would mark particular sedimentary layers with particular ages. Or we could use carbon-14 dating of fossils like plant or shell material. So then we have this outcrop of mostly sedimentary layers, but then we do have this basalt intrusion here. So we can examine the positions of the sedimentary rock layers in relation to igneous rock intrusions or volcanic ash, things like that, which we actually do have up here. So this is volcanic ash. This is basalt intrusion, and then this is granite, which is a pluton. And those are all dated, okay? Because you can date igneous rocks. So then we can estimate the ages of the sedimentary rock layers that are making up the rest of the outcrop. But again, it would just be older than this number, younger than that number. It wouldn't be exact ages of the sedimentary rocks. So for example, the age range of the Paleocene sandstone, which is here, this is the Paleocene sandstone. We could figure out the age range in millions of years by looking at the volcanic ash and the igneous intrusion. And then we could get the age range of the Cretaceous sandstone down here using the granite pluton and the igneous intrusion. Okay, good. So we have, it's going to be older than 50 million and younger than 80 million. Okay, again, because you have the volcanic ash layer here, the Paleocene sandstone is below that. So it's older than 50, but it's above the basalt dike, which is 80 million. So because it's above that, it's younger. So it's between 50 and 80, okay? And then we have the age range of the Cretaceous sandstone. So let's do that one. Yes, that is correct. So we have between 80 and 125. Yes, because we have the granite down here, which is 125 million, and then the basalt dike, which is 80. And then here's the Cretaceous sandstone. Okay, good. So let's move on to look at the geologic time scale. So this is the geologic time scale, and it goes from 0 million years to 4.560, which is really 4.56 billion. And then when you come all the way up to the top, it's broken, it branches out into this more detailed piece of time scale here. And then this top part is broken out into a more detailed sections. So the next part of the lecture, we're going to go through lots of details about all of this Earth history.